Hello, I welcome you all to this another interesting screencast. The problem reads, draw the shear and the moment diagrams for the beam. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. Right, we have a simply supported beam with a distributed load on half the span, and then we have a point load which is placed 2 meters from B. Let's draw the free body diagram. We're going to have a vertical reaction like so, and then a horizontal there. And later on at the roller, we're going to have a vertical reaction like so. Applying the equations of equilibrium, we'll start with joint A, support A. So summation of moments about point A equal to 0. That's clockwise being our reference. We have a minus moment 10 by 8, right? Then here we're going to have an equivalent force. This is rectangular load with a constant intensity. So for us to find an equivalent force, we just have to find the area under this loading diagram, which is 2 times 5, which gives us a 10 kilonewtons. And this load is positioned at 2.5 meters from A, right? Great. So we also have another negative moment, which is 10 times 2.5. What else? We also have a positive moment by times 10 equal to 0. Therefore, our by will give us, scrap our calculator, minus 10 by 8, minus 10 by 2.5, and then this divided by 10. So it gives us a 10.5 kilonewtons. Minus 10 by 8, minus 10 by 2.5, okay, and then we have divided by 10, right? And then we move on to another equation, summation of forces in the y direction. What we have? We have ay minus 10 plus by equal to 0. We've already calculated what by is, which is this one here. So what we just need to do is to find ay. Ay will be equal to minus 10 plus 10.5, right? So this gives us 9.5 kilonewtons. And then we have summation. We have summation of moment in the x direction. We already know what the solution, what the answer is going to be, because we don't have any loading in that direction, right? So ax will just give us equal to 0. Great. So we have this equal to 0. Use red. This equal to 0. Ay equal to 9.5 kilonewtons, and by equal to 10.5 kilonewtons. All right, let's get rid of this stuff so that we we work on the problem. If we decided to do the sectioning, we would have had 3 intervals. We would have had this interval 1, and then we would have had this other interval, and then finally this interval. But we are not going to do the sectioning. Instead, we are just going to use the differential equations, which are dv dx, okay, gives us negative loading, and then dm dx is equal to v. We're going to use just this to draw the shear and bending moment diagram. So to start with, we are going to first draw just these lines here. This represents, these are going to be this we have for the load, the first one, then the shear force diagram and the bending moment diagram. Okay, positive up, negative down, 0 there, positive up, negative down, 0 there. All right, this point here is A and this point here is B. Okay, we have a reaction here of 9.5 kilonewtons, and then we have another one there of 10.5 kilonewtons. All right, and then we have a distributed loading, let's say up to half the length of the beam, somewhere there. Okay, and this is constant distributed load or rectangular, which is 2 kilonewtons per meter. We also have a point load somewhere there, a point load or a concentrated load of magnitude 10 kilonewtons. All right, and then let's include the dimensions of the beam. So from A to where the rectangular load ends to the point load, and finally to the roller. There we go. So this is 5 meters, right? And this is 3 meters. Oh, this is not, yeah, and then this finally is 2 meters. Okay. Point load is 2 meters from D, right? Great. So now let's start the work. So at A, for the shear force diagram, we have a 9.5, okay, shear, which will make this go up by 9.5, somewhere there. Let's end there. Let's assume this is our 9.5. Okay, maybe it has gone too high. Maybe we bring it up to here. Great. Okay, so this is our 9.5 kilonewtons. And then we have a distributed load of intensity 2 kilonewtons per meter. So we expect this 9.5 to reduce, okay, at the rate of 2 kilonewtons per meter. Right. Some principles that we can use. We have the load, okay, which is negative, and it is constant, right? Therefore, we expect the slope for shear, okay, shear slope also to be negative, okay. It will be negative with a constant value, right? Of course. Let's check it out. So now, if we have 9.5, we expect this to reduce. So we are going to say 9.5 minus 2 kilonewtons. Will convert it to an equivalent force over the length of 5 meters. So it will be 2 by 5. What does this give us? So it's 9.5 minus 2 times 5. So we expected minus 0.5. So at this point here, let me just draw these lines because we expect change of behavior where the load begins and where it ends. Alright, so we expect a negative coming down like this. Let's say this is our negative here. This is negative 0.5. So we are going to have a straight a decline, okay, a negative slope. All right, with a constant value, right? Okay, this. All right, and this value here is 0.5 kilonewtons. And then from this point, let me call this point here as C, and then this one D. Okay. Okay. So the moment we move to the right of C, we realize that we do not have any loading from C to D in between this interval. Right. So again, we know this relationship. Let me just wrap this. We know that where we have the loading equal to 0, okay, we expect the slope, shear slope, or the slope for shear to also be equal to 0. Right, so from C to D, we just expect a straight line with a 0 slope, right, up to there, just before the point load. Okay, all right. Then the moment we reach the point load, okay, we expect this particular shear slope, okay, or we expect this shear here to change, okay. It is going to be reduced further by a 10 kilonewton. So we are going to have a scenario like this where we have minus point, okay, minus 0.5 minus 10. This gives us a minus 10.5. Okay, so we expect a downward movement from this point, okay, by 10 kilonewtons. Let's say 10 kilonewtons comes up to there. Okay, so this is the final value here is 10.5 kilonewtons. Right, and then between D and B again we have 0 0 load. We also expect a slope to have a constant of 0. I mean to have a slope of 0, sorry, to have a slope of 0. So again, we are going to expect a straight line like so, just before B. The moment we reach B, we expect this particular slope to be increased by a value of 10.5. So we have minus 10.5 plus 10.5, which gives us 0. So our shear finally closes, which we expect, like so. Great. So our shear diagram is finally complete. This is how we expect our shear diagram to behave. It has to close. Okay. So it has finally closed. This point is 10.5. This is 0. And this is 0.5. So this region is all minus. All this is all minus shear, and then this region here is plus. Great. Okay, so now we are not done. There is one point that we need to find. We need to find this point, this one here, where shear is equal to 0. We know that when shear is equal to 0, okay, then that is the point where we are going to have the maximum. When shear is equal to 0, okay, when shear is equal to 0, it means at that particular point, that's where we are going to have the maximum moment, okay, this point, okay, right. So now we need to find this by using similarities of triangles. Okay, so what we can do is we do have a triangle like this. Okay, we have a triangle. Okay, this one, you've seen this one. Okay, so we have that. So what we need to do now is to just find that length. We need to find this length. Okay, so for now we are going to find this length here. Okay, all right, so let's do it. So we have a 9 plus 5 plus 0.5. Okay, so divided by the whole length from A to C, which is 5, is equal to the length of this smaller triangle there, which is just 0.5, then divided by this length we're just going to call x, right? And therefore our x is going to be equal to let's punch our calculators. 9 plus 5 9.5 plus 0.5, of course, is 10, and divided by 5, which is a 2. Okay, and then finally, so we have x is equal to 0.5. Okay, 0.5 divided by 2, which is equal to 0.25. So this one is 0.25. Okay, so if it is 0.25, we therefore know the length for this one. This one is going to be equal to so 9.5 plus 0.5 divided by 2, 0.5, right? Yes, 0.25. So we have 5 meters. 5 minus 0.25, we have this one as a 4.75 meters. So we have that information, so we'll be able to use it to do to compute our maximum moment. So let's move to the figure for, the diagram for the bending moment diagram. Okay, there we go. So what do we have? The shear here, let's go for the shear. Okay, the shear is positive, is a portion that is positive and is decreasing. Okay, that is from 0 to 4.75. Therefore, we expect the slope for the moment to also be positive and decreasing, right? So which one would you go for? Okay, this is positive and this is positive. Which one? A red or a green? Which one? Of course both of them are positive, but which of the two is decreasing? The green or the red? Of course, see, the green is the one that is decreasing while the red is increasing. Great, so we are going to go for the green. So we expect this behavior, it decreases, is positive but decreasing slope up to somewhere there. Okay, somewhere there. All right. Okay, so now we are in this other interval, okay, of length 25 from the point where shear is equal to 0. Okay, this point here. All right. So what do we have? We have shear that is negative but increasing, right? That's fine. So if this is the case, then we expect the slope for moment to also be negative but also increasing. Okay, right. So it will be a parabolic, only that it will be negative. It will have a negative slope but increasing. So it will face down like this. Let it not, it will be something like that up to there. All right. Okay. So this one will be parabolic but with negative slope, negative increasing slope. Right. And then the moment we reach at D, the conditions change. What do we have at D? From C to D, the slope, I mean the shear. Shear, okay. The shear itself here is it is negative, okay, and constant, right? So we expect the slope for moment also to be negative constant, to have a negative constant. All right. So we expect this to be from this point, okay, it is going to be a negative value, but we need to calculate it, right? All right. Okay, we'll calculate it later on. Okay, let's calculate these values. Okay, we'll come and calculate them later on. So it's going to be something like this. All right, let's imagine it's going to be like so. Okay, up to there. All right, and then from D to B, the slope, I mean shear, is negative and it is also constant from D to B. We expect the slope for the moment also to be negative constant. So again, this is going to be another straight line. Okay, this one should be more negative, right? I mean the increase should be more higher than the other one, right? Yes. So now let's calculate these values. Let's start with the maximum. So we are going to use this particular um, shear diagram. We know that the area under the shear diagram gives us the moment, so let's use that one. So maximum moment will be equal to half times 9.5 times 4.75, and this gives us 0.5 by 9.5 by 4.75. So we have a 22.56. This one is a 22.56. Practice longer. 5625. I'll just write the whole lot of it. 5625 kilonewton meters. 0.5 times 9.5 times 4.75, 22.5625. Right. And then this one here is going to be equal to moment is equal to half. All right. So there will be a decrease of moment from this end to there. Okay, so we need to have it subtracted, right? So this is going to be equal to moment at that point will be equal to moment at that point will be equal to 22.5625 minus half times half times 0.5 times 0.25 is going to be equal to 22.5625 minus 0.5 times 0.5 times 0.25. So this value here will be 22.5 kilonewton meters. Okay, difference is quite minor, right? But it's there. And then finally this one here, we are going to get, we are subtracting, so that one there, this one here is equal to, so we can either use this part or we can use the whole lot of subtract at every point. Okay, so we are going to confirm using, let's use the left part. Okay, so this is going to be equal to 22.5 minus 3, that's the area for this one. Okay, 3 times 0.5. What do we get? 22.5 minus 3 by 0.5. So we get a 21. So this one we expect it to be 21 kilonewton meters. We expect to find the same if we used this area here. Let's try it. M will be equal to 10.5 times 2. Okay, 10.5 times 2 gives us 21. So it's the same value, right? Okay, I think that is about it. And this moment here is positive, right? I guess we are done, and I hope the video was helpful. If it was, give me a thumbs up, like my video, and continue sharing my videos. Bye bye, and see you in my next screencast.